Dear students, in the previous video, we discussed the main postulates of valence shell electron pair repulsion theory, and we discussed the geometry of molecules containing bond pairs only using VSEPR theory. Today, we will discuss the geometry of molecules containing bond pairs and lone pairs, and we will see how the presence of lone pairs causes distortion of the geometry of molecules. Presence of lone pairs cause distortions from the regular geometry of arrangement of the electron pairs around the central atom because of their mutual repulsions. First, let's see the case of Stannis chloride SnCl2. The tin atom has this configuration. It has 4 valence electrons, as you can see here, 5s2, 5p2. So out of these 4 valence electrons, 2 of them will form bond with the 2 chlorine atoms. So it will have 2 bond pairs. And the remaining 2 electrons form 1 lone pair on the tin atom. And according to VSEPR theory, in order to minimize the repulsion between the lone pairs and bond pairs, they try to stay as far apart as possible. So here there are 3 electron pairs in total, 2 bond pairs and 1 lone pair. So when we have 3 electron pairs, the expected geometry will be trigonal planar. So we expect a trigonal planar geometry for SnCl2. But one of the corner is occupied by a lone pair instead of an atom. So this lone pair distort the geometry from the trigonal planar to a bend shape, as you can see here. It may be called a bend shape or V shape or an angular shape. For a trigonal planar geometry, the normal bond angle is 120 degree. But here, due to the repulsion between the lone pair and the bond pair, the bond angle decreases from 120 degree to 95 degree. So SnCl2 will have a bend shape and the bond angle being 95 degree. One of the corners of the trigonal planar is occupied by the lone pair. Next, let's see the geometry of water molecule. Oxygen is the central atom here. It has 6 valence electrons. Out of the 6 valence electrons, 2 electrons are shared with the 2 hydrogen atoms, so that it will have 2 bond pairs. The remaining 4 electrons are on the oxygen atom. So that will form 2 lone pairs. So we have 2 bond pairs and 2 lone pairs. So total 4 electron pairs. If we are having 4 electron pairs, the expected geometry according to VSEPR theory will be a tetrahedral geometry. But since in the tetrahedron, 2 of the corners of the tetrahedron are occupied by the lone pairs. And we know that a lone pair repulsion is very much greater than a lone pair bond pair repulsion. So in this molecule, that is in water molecule, you can see lone pair repulsion as well as lone pair bond pair repulsions. So because of these repulsions, the water molecule will assume a bend shape, a V shape or angular shape as in the case of SnCl2. But here the bond angle is 104.5 degree instead of the normal bond angle of 109 degree 28 minutes as in the case of a tetrahedron. So in the case of water molecule, though we expect a tetrahedral geometry due to the presence of 4 electron pairs, but the actual geometry is a bend shape or V shape because out of the 4 electron pairs, only 2 are bond pairs and the other 2 are lone pairs. And the bond angle decreases from 109.5 degree to 104.5 degree. Similar geometry can also be seen in other molecules like Cl2O, F2O, NH2- ion, etc. And next is the ammonia molecule. Nitrogen has 5 valence electrons, and out of these 5, 3 forms bond with 3 hydrogen atoms, so they will form 3 bond pairs. And remaining there are 2 electrons on the nitrogen atom forming 1 lone pair. So total 3 plus 1 equal to 4 electron pairs. And if you are having 4 electron pairs, then we will expect a tetrahedral geometry according to VSEPR theory. Again, since one of the electron pairs is a lone pair, there will be a distortion in the geometry from the tetrahedral to trigonal pyramidal. And here also the bond angle decreases from the normal tetrahedral angle of 109 degree 28 minutes to 107 degree. As you can see here, the bond angle, that is the HNH bond angle, is 107 degree because of the trigonal pyramidal geometry. In NF3 also we can see similar trigonal pyramidal structure like ammonia. So ammonia molecule, we expect a tetrahedral geometry, but due to the presence of lone pair, the geometry changes to trigonal pyramidal with a bond angle 107 degree. Now next is Sf4. Sulfur atom has 6 valence electrons. Out of these, 4 electrons form bond with 4 fluorine atoms. So the number of bond pairs is 4. The remaining 2 electrons on the sulfur atom will form one lone pair. So there will be a total of 5 electron pairs for the Sf4. For 5 electron pairs, we expect a trigonal bipyramidal geometry according to VSEPR theory. But again, out of these 5 electron pairs, one is a lone pair. So due to the presence of lone pair, the geometry becomes a seesaw shape, as you can see here. And in this molecule, the lone pair occupies the equatorial position. The bond pairs occupy the remaining 4 positions. And the FSF bond angle will be 173 degree. So in Sf4 molecule, there are 4 bond pairs and 1 lone pair on the central atom. Central atom is sulfur. And the expected geometry is trigonal bipyramidal, but due to the presence of lone pair, it changes to a seesaw shape. So Sf4 has a seesaw shape. Now next is the geometry of Clf3. Chlorine atom has 7 valence electrons, and out of these 7 valence electrons, 3 forms bond with 3 fluorine atoms. So the number of bond pairs is 3, and there are 4 electrons remaining on the chlorine atom. So they will form 2 lone pairs. As you can see here, 2 lone pairs. So total number of electron pairs is 3 plus 2 equals 5. So in this case also we expect a trigonal bipyramidal geometry. But since there are 2 electron pairs on the chlorine atom, the geometry changes to a T shape, as you can see here, the T shape of Clf3 molecule. The FClF bond angle is 87.4 degree. And for this T shape, the theoretical value is 90 degree. So here the bond angle is slightly less than 90 degree and it is 87.4. And this decrease is obviously due to the repulsions between the lone pairs, which are stronger than the bond pair repulsions. So the geometry of Clf3, we expect it to be trigonal bipyramidal, but due to the presence of 2 lone pairs on the chlorine atom, the geometry changes to T shape. Here the lone pairs occupy the 2 equatorial positions, and the angle between each axial bond and the equatorial bond is 87.4 degree. Next is the geometry of an inner halogen compound IF5. We know that iodine has 7 valence electrons. So out of these 7, 5 electrons will form bond with the 5 fluorine atoms. So the number of bond pairs is equal to 5. The remaining 2 electrons will form one lone pair. So total number of electron pairs is 6. According to VSEPR theory, if there are 6 electron pairs, the preferred geometry will be octahedral. So we expect an octahedral structure for IF5. But due to the presence of a lone pair on the iodine atom, the geometry becomes a distorted square pyramidal, as we can see here, a distorted square pyramidal. Here you can see an actual square pyramidal structure. But in the case of IFI, you can see that the two fluorine atoms are slightly bent upwards. And this is known as a distorted square pyramidal. In IFI, the electron pair, the lone pair of electrons on the iodine atom will push the two fluorine atoms so that it becomes a distorted square pyramidal in shape. So in IFI, due to the presence of 6 electron pairs, we expect an octahedral arrangement. But one corner of the octahedron is occupied by the lone pair so that the molecular geometry becomes a distorted square pyramidal geometry. And the distortion is due to the repulsion between the lone pair and the bond pair. And the FIF bond angle is 81.9 degree. The normal octahedral angle is 90 degree. So here it is slightly less than 90 degree. Now let's see the molecular geometry of xenon fluorides. So we have Xcf2, Xcf4 and Xcf6. In these three molecules, there are varying number of bond pairs and lone pairs. And let's see how the difference in the number of bond pairs and lone pairs affect the geometry of these molecules. First is Xcf2. Now that xenon is an inert gas and it has an octet configuration. That means xenon has 8 valence electrons. Out of these 8 valence electrons, 2 electrons form bonds with the 2 fluorine atoms. So the number of bond pairs is 2. There are 6 electrons remaining on the central xenon atom. These 6 electrons form 3 lone pairs. So we have 2 bond pairs and 3 lone pairs. So total 5 electron pairs on the central atom. According to VSEPR theory, if there are 5 electron pairs, we expect a trigonal bipyramidal geometry. But since there are 3 lone pairs of electrons, the geometry changes to a linear one with a bond angle 180 degree. The 3 lone pairs occupy the 3 equatorial positions, as you can see here, and the fluorine atoms occupy the axial position. That is, the 2 bond pairs occupy the axial position, one above and below the plane, and the 3 lone pairs occupy the equatorial position. So instead of trigonal bipyramidal geometry, the geometry of Xcf2 becomes linear with a bond angle of 180 degree. Next is Xcf4. Xenon has 8 valence electrons. And 4 of these electrons form bonds with 4 fluorine atoms. So the number of bond pairs is 4. And the remaining electrons will form 2 lone pairs. So the total number of electron pairs will be 6. And according to VSEPR theory, if there are 6 electron pairs, we will expect an octahedral geometry. But since there are 2 lone pairs on the central atom, the geometry deviates to square planar, with the lone pairs occupying the axial positions, and the bond angle will be 90 degree. So in Xcf4, though we expect an octahedral geometry, due to the presence of lone pair, the geometry becomes a square planar, and in order to minimize the repulsion, the lone pairs occupy the 2 axial positions, and the remaining 4 coplanar positions are occupied by the 4 bond pairs, that is by the 4 fluorine atoms. And the last one is Xcf6. Out of the 8 valence electrons in the xenon atom, 6 electrons will form 6 bonds with the fluorine atom. So number of bond pairs is 6, and the remaining 2 electrons form 1 lone pair. According to VSEPR theory, if there are 7 electron pairs, here you have 6 bond pairs and 1 lone pair. So total 7 electron pairs. And if there are 7 electron pairs, we expect a pentagonal bipyramidal geometry. But since one of the electron pair is a lone pair, then the geometry becomes a distorted octahedral, with the lone pair occupying the trigonal face. And the distorted octahedral geometry is believed to have the lowest energy configuration, but we cannot always say that this is the exact configuration of Xcf6 because this molecule is a fluxional molecule. A fluxional molecule means the geometry will be changing rapidly with time. That is, the fluorine atoms may shift their positions and also the lone pair may change from one phase to another phase. So such a molecule is called a fluxional molecule. So in Xcf6, the molecule is having a distorted octahedral geometry. So today we have seen various examples of the geometry of molecules containing bone pairs and lone pairs, and how these lone pairs causes deviation from the actual geometry.